The universe is a false state, the bubble that deletes everything. Her coffee rippled, then the table, her hand, the air, gone. No heat, no flash, no scream. A frontier hit the room and rewrote the instructions for matter, and that was it. If a true vacuum bubble formed anywhere in our cosmic neighborhood, it would sprint at near light speed and erase chemistry on contact. There's no siren, no halo, no sky turning strange before it arrives. You don't outrun information, you don't even see it coming. Our senses are fast, but they're an interface built for lunches and doorways, not for cosmic patch notes. If the universe really is perched on a temporary state, this isn't fiction. It's the quietest catastrophic update imaginable. Complete, instant, and indifferent. We're not here for sci-fi pyrotechnics. We're here because measurements of the Higgs boson and the top quark put us close to a ledge where the vacuum might be long-lived, but not final. That's the first mystery. Are we standing in a shallow dip, not the deep valley? From there, the stakes escalate. You'll see how a bubble would form, why its wall races at near light speed, and what flips inside it. Masses, forces, the very grammar of atoms. We'll separate collider folklore from the reality that nature slams higher energy collisions into our atmosphere every day. If vacuum decay were easy to trigger, the universe had billions of years to try it. We'll trace the odds, not with melodrama, but with the math of decay rates measured against the sheer volume of space-time. We'll compare this wildcard to the other endings on the board. Heat death, big rip, crunch, and ask which clocks reach us first. We'll bring the scale down to a human room, a human breath, a human decision that still matters even when the horizon is uncertain. Here's the twist we'll keep coming back to. Your perception is a fast, lossy user interface, not a microscope for reality. That makes the most unsettling part make sense. There may be no sensory prelude to a vacuum flip because our interface wasn't built to preview new physics. Along the way, you'll hear the honest limits, where the standard model runs out of runway, where high-order corrections and top-mass uncertainties keep our verdict humble, and where new physics could rescue stability or deepen the drop. You'll leave knowing what physicists actually worry about, why most sleep fine anyway, and how to live with a universe that might one day change state with no farewell. To understand the bullet, we need the gun, the energy landscape itself. The universe on a ledge, false versus true vacuum 101. To understand a false vacuum, swap cosmic poetry for a hill with valleys. The field sits like a ball. The deepest valley is the true vacuum. Anywhere else is just good enough. Our universe looks calm because the ball has settled into a dimple. It isn't the bottom. There's a ridge between here and the lower valley. Classically, the ball can't climb over. Quantum mechanics, however, doesn't ask permission. It tunnels. Tunneling is the weird permission slip of the quantum world. Instead of rolling over the ridge, a tiny patch of field slips through the barrier, landing in the deeper valley. That patch is a bubble of true vacuum. It's not a metaphor. It's a region of space where the field's value, and therefore the energy of empty space, has changed. If the bubble is too small, surface tension crushes it. Get past the critical size, and the interior's lower energy wins. The wall accelerates outward, and within a blink, it's moving at nearly light speed. Here's why the stakes are human. Fields set masses. The Higgs field's value is why electrons weigh what they do, and why atoms have sizes that chemistry can use. If the vacuum flips to a configuration with a different Higgs expectation value, electron mass changes. That tiny tweak shatters everything built on it. Orbitals don't hold. Molecules don't bind. Nuclei may not be stable under the new force balance. Inside the bubble, physics isn't us but inconvenient. It's not us at all. And here's the freaky science twist. Your nervous system isn't built to notice a frontier like this coming. Perception is an evolutionary interface that highlights fitness cues, edges, faces, movement, and hides source code. It gives you useful icons, not the kernel logs. A vacuum flip doesn't announce itself in those icons. No smell, no color shift, no loading screen. That's not a special effect. It's the point of an interface that optimizes survival, not truth. People ask about explosions. There isn't one in the way our instincts expect. No fireball racing ahead of a shockwave. The bubble wall is the front. It is the event. And because it moves at the maximum allowed speed for cause and effect, There's no advance warning signal that can outrun it. One instant you participate in this rulebook. The next, you're rewritten. Or more precisely, there is no you under the new constants. That's what instant means here. Not a fast process unfolding, but a boundary that replaces the process entirely. But if the field is lower energy inside, doesn't that pull on things? The bubble's energy accounting is subtle. There's the bulk energy difference inside and a positive energy stored in the wall. In many models, those balance in a way that keeps gravity from doing anything dramatic at the front. The wall just goes. The universe doesn't bulge or wrinkle as a tell. You can't spot a lensing signature and whisper, "It's coming." If the front is in your future light cone, it arrives without herald, and your interface never had a mode for incoming new vacuum anyway. Does this mean we're in danger tomorrow? The word that matters is metastable. It means can last for an absurdly long time. Think of supercooled water that refuses to freeze until a seed crystal appears, then flashes to ice. The water wasn't unsafe until it was. Our vacuum, if metastable, could have a lifetime vastly longer than the current age of the universe. The decay rate is quoted per unit volume per unit time, a number so tiny that even when multiplied by everything, everywhere, everywhen, the expectation can still be not for eons beyond black hole evaporation. Tiny isn't the same as zero. It's the physics way of saying, not inevitable on our clocks, but not forbidden on the universe's. People also ask whether colliders can push the ball. The answer lives in the sky. Ultra-high energy cosmic rays hit our atmosphere with energies far beyond anything we can build. And they've done so for billions of years across galaxies and gas clouds and stars. The universe has run the experiment at scale. If a collision could seed the bubble's front would already be here. Safety studies lean on that fact. Humans aren't the first to smash particles together. There's one more step. The landscape's shape can change with scale. As you probe to higher energies, couplings run and the effective potential tilts. That's why the Higgs mass and the top quark mass matter. They steer the calculation towards stability, metastability, or catastrophe. Current best fits? The ledge scenario, metastability is favored, with uncertainties that keep theorists honest. Add new physics, an extra field, a symmetry, a heavier partner, and the ridge thickens or the valley disappears. The ball gets safer or the map redraws itself. Meanwhile, the analogy holds. A ball settled, a ridge high, a deeper valley possible. Quantum mechanics gives the only door. If, somewhere, sometime, a patch slips through and grows past critical size, a frontier begins and erases the canvas as it goes. No smoke, no flame, no second chance. Metastable doesn't mean scared, it means clear-eyed. We live well in a calm dimple that might not be forever. Next, we ask the measured question. Given what we know about the Higgs, how close to that ridge are we really? The Higgs Clue, metastability in the standard model. To see how close we are to that ridge, we need the one field we've actually measured, the Higgs. In 2012, the LHC pinned its mass at about 125 GeV. That single number, together with the top quark's mass, sets the mood of our vacuum. Not poetically, mathematically, by deciding how the Higgs self-coupling lambda runs as we slide to higher energies. Running is quantum bookkeeping. Interactions aren't fixed. They evolve with the energy scale. You can think of it like checking the slope of our valley with a different ruler each time. At the electroweak scale, the Higgs potential is a neat bowl. But as we move to much higher scales, quantum corrections from particles that couple strongly to the Higgs, especially the top quark, pull on the shape. If the pull is strong enough, lambda goes negative at some high scale. A negative lambda means the bowl flips to a brim. Not disaster now, but a sign there's a deeper valley far away. Here's the punchline. Physicists keep returning to. Take the measured Higgs mass, fold in our current best estimate of the top quark mass, and run the equations. The curve grazes 0, around 10 to the 10 to 10 to 10 to 12, GeV, and dips below thereafter. That points to metastability, not absolute stability. In other words, the dimple we live in is real and deep enough to last absurdly long. But it probably isn't the global minimum. Why the top quark? Because it talks loudly to the Higgs. Its Yukawa coupling, the strength of that conversation, drives the correction that drags lambda downward as we climb in energy. Shift the top mass by a few hundred MeV, and the fate line edges around. That's why experimentalists obsess over how we define top mass. The Monte Carlo mass pulled from collider events isn't trivially the same as the pole mass used in precise theory runs. Small definitional differences ripple into the stability diagram. Meanwhile, theorists sweat the loops. Higher order corrections, 2-loop, 3-loop, aren't garnish. They're essential to nail the crossing point, where lambda turns negative, and to quantify the uncertainty. Add in the strong coupling constant, alpha psi, and you've got a three-way tug-of-war. Nudge any of them within today's error bars, and the stability map shifts a little, but the central picture holds. Our coordinates sit in the metastable wedge with a decent margin. That doesn't mean tomorrow's update flips the verdict to unstable. It means the band of uncertainty is honest. Current global fits favor a long-lived false vacuum, comfortably outlasting stars, galaxies, and black hole evaporation by a laughable factor, while leaving room for two outs, either absolute stability if the true top mass skews lower, or an earlier dip if it skews higher. Neither swing is likely given present data, but the door isn't locked. There's another layer, beyond standard model physics. New heavy fields, extra Higgs doublets, supersymmetric partners, or even higher dimensional operators from unknown UV physics all feed back into the running. Some add a prop that keeps lambda positive. Others poke an extra hollow into the potential at high scales. In practice, many natural extensions stabilize the vacuum by shoring up the ridge, while some exotic ones deepen the far valley. Metastability is a standard model verdict, contingent on no new players. Add players and the map updates. Cosmology adds a sanity check. If our vacuum were too fragile at inflationary energies, quantum jitters back then could have kicked regions over the ridge. We're here, so either the parameters allow survival with high probability, or new physics stiffen the potential in the early universe. That's not a paradox, it's a consistency constraint. Any viable model has to let a metastable vacuum ride out a violent childhood. So what do physicists actually worry about day to day? Precision. Better extractions of the top mass from methods less tied to Monte Carlo tuning. Tighter determinations of alpha eds. Improved higher loop calculations that shave theory error. Each increment shrinks the band on the stability plot and tests how accidental our location is. It's the oddity that nags. Why are we so close to the boundary? Coincidence, selection, or a hint of structure we haven't seen? And yet, this is the quiet kind of worry. The computed lifetime for decay, given our best inputs, dwarfs any clock we live by. Metastable doesn't mean anxious. It means secure on human, stellar, and even black hole timescales, while refusing the word eternal. The Higgs number we measured is the breadcrumb that got us here. A universe calm enough for atoms, perched near a line that teaches humility. From this ledge, the next question is concrete. If the patch ever flips, what exactly flips with it? What changes inside the bubble? Physics patch notes. Open the notebook to the only release note that matters. Vacuum updated. Everything downstream takes its cue from that line. The Higgs field's expectation value, its baseline, sets particle masses. Change that baseline, and every mass that came from the Higgs changes with it. It's not a cosmetic tweak, it's the font of reality swapped mid-sentence. Start with electrons. Their mass is YE times the Higgs value. If the Higgs settles lower, electrons get lighter, higher, heavier. Either way, atomic structure isn't a gentle slider. Atomic sizes scale with 1 ME alpha. Tweak ME and the Bohr radius jumps. Raise electron mass and orbitals shrink. Lower it and they balloon. But bigger or smaller isn't the point. The point is binding. Energy levels shift. Ionization energies change, and the spectrum that stabilizes chemistry gets taken apart. Under many true vacuum scenarios favored by simple standard model running, the Higgs value plummets far enough that the potential turns catastrophic. The new balance doesn't support the atoms we know. You don't lose a shelf of the periodic table. You lose the notion of one. Then the nuclei. The strong force is set by QCD, and its scale, len QCD, is mostly independent of the Higgs, but nucleon masses and beta decays care about quark masses that do come from the Higgs. Change those, and you change the lightest stable nucleus, the thresholds for fusion, and whether protons remain the ground state baryon. In some patches of parameter space, the neutron becomes lighter than the proton. In others, the deuteron unbinds. In still others, d-neutrons bind where they didn't before. The tight triangulation, quark masses, electromagnetic repulsion, nuclear attraction that makes carbon and oxygen viable is delicate. Tilt one axis and the staircase of elements collapses. If nuclei don't bind, there's no chemistry to salvage. If they bind in unfamiliar ways, you get a periodic table with letters we can't read. Forces don't vanish, but their apparent strengths shift when masses move. Electroweak mixing angles can land differently. The effective Fermi constant changes. Weak interaction rates speed up or stall. Radioactive decays that seeded heat in planets and elements in stars might not happen, or happen too fast for any structure to persist. The fine structure constant, alpha, may or may not move depending on deeper physics. But even if alpha stays, the mass ratios that set molecular energy scales don't. Vibrational modes misalign. Covalent bonds refuse to form. Van der Waals forces rule an empty kingdom. What about light itself? Photons are still massless if gauge symmetry remains, but transparency depends on media that no longer exist. Solid matter owes its solid to electron seas and lattices. If electrons can't bind, there are no solids, no conduction bands, no insulators, no semiconductors, no glass to shatter, no metal to bend, no categories at all. In many models, even if some bound states persist, the energy gaps sit in the wrong places. Heat capacities, thermal conductivities, refractive indices. Every material's constant you've ever looked up becomes undefined for lack of material. People ask if there's any life inside. That's the wrong scale. Start with structure. To have complexity, you need at least two stable hierarchies, bound nuclei and bound electrons. Then you need forces that let many body systems explore huge combinatorial spaces without falling apart instantly. The vacuum flip doesn't retune those knobs a little, it replaces the soundboard. Even the long-range gravitational game changes because the equation of state of whatever replaces matter alters how lumps form. If baryons are unstable, the only long-term actors are radiation, neutrinos, and whatever dark sector exists, if it even couples the same way. Gravity still curves space-time, but with nothing clumpy to curve it around, the cosmos is smooth where we were bumpy. There's a subtlety about energy that tempts hope. Lower vacuum energy sounds good, but that bookkeeping is global. Locally, the positive energy in the wall and the negative offset inside can cancel gravitationally, so the bubble front leaves no obvious tidal signature. After it passes, you're left with a new baseline energy density and new field values. If the true vacuum is anti-de Sitter, negative vacuum energy, the interior isn't just different, it's doomed to collapse. Space-time crunches on short timescales. If it's a lower, still positive vacuum, expansion continues, but with alien rules. Either way, there's no bridge. No adapter layer that lets old atoms handshake with new constants. Microstories make it personal. A hard drive's magnetization needs exchange interactions between electrons in a crystal. Gone. A coffee cup's solidity is Pauli exclusion expressed through bands. Gone. A heartbeat is ion channels, protein folding, water's hydrogen bonds. Every piece is an electron mass, a nuclear mass, a coupling, all set by a field that just took a new value. It isn't fire, it's not breaking, it's replacement. So the patch notes read, particles remapped, masses reassigned, spectra redrawn, matter definition withdrawn. No explosion, no ash, no aftermath to sift. Just a different vacuum occupying the same coordinates, as indifferent to our categories as the old one was generous. And with that, the only remaining question is motion. How does that wall travel? And can anything in principle move faster? No. Which is why, if it starts in our future, we never see the release notes arrive. We only see the new version already running. The front arrives at light speed, no warning, no escape. You can't outrun causality. That's the core of this chapter. The bubble wall isn't a shockwave you can beat by hopping on a plane or digging a bunker. It's the frontier of new rules, and it moves as fast as cause and effect can move through space-time, at essentially light speed relative to what it passes. If the flip starts anywhere in our future light cone, the front and the message are the same thing. There's no precursor, no rumble, no growing glow on the horizon. One moment, the equations that make you possible apply. The next, they don't. People want to know if cosmic expansion helps. It doesn't. Expansion stretches distances between faraway galaxies, but locally, where you and the wall meet, expansion isn't a shield. The front advances through space itself, not across a fixed background like wind across a field. In general relativity terms, expansion can drag distant regions apart faster than light without violating causality. But a causal front moving through the fabric still outruns any local signal. Given a start in our reachable future, it gets here. Given a start outside, it never does, and we never learn it happened. Could we detect it just before it hits? Some lensing, some free energy anomaly, a whisper in a detector? The best answer from models is no. The wall's energy budget is balanced. Lower bulk energy inside, positive surface energy in the wall. That sum can cancel gravitationally so thoroughly that there's no distinctive tidal signature ahead of it. No time delay in starlight betrays an edge. No neutrino spike announces a boundary. You don't watch the sky get weird. You watch nothing at all, and then the nothing changes definition. What about the bubble's shape and speed? Classical pictures make it a sphere expanding from a nucleation point, its radius growing like a movie reel. In a real quantum field theory, the front accelerates rapidly to a terminal velocity arbitrarily close to light speed. The details of friction, how the wall interacts with ambient particles, matter in hot early universe transitions. Today's universe is cold and thin. There's almost nothing to slow it. The difference isn't academic. In the early cosmos, a bath of particles can load the wall. In our epoch, the wall glides with almost no drag. For us, it's the purest kind of instant, a boundary that replaces the system faster than any warning can propagate. Could the first bubble stall? Not if it crosses the critical size. Below that, surface tension collapses it. Above that, the interior's energy advantage drives growth. Once supercritical, the math doesn't allow a graceful stop. In toy models, bubbles can collide and merge, wrinkling walls and radiating energy into the fields they couple to. But that's a story for an observer outside the front. Inside, you don't keep a journal. Outside, you never see the collision because light from the interaction can't outrun the wall either. The drama is real and completely unobservable to us. Micro stories bring it down to a room. The coffee ripples you saw earlier weren't real ripples. They were the last moment you mapped onto a familiar reference frame. In practice, no ripple arrives. A hard drive doesn't glitch, it's just not a hard drive anymore. A hospital monitor doesn't flatline. There are no ions, no channels, no conduction to make a line. A telescope pointed at a distant cluster doesn't catch the front approaching. The stream of photons it collects ends midstream. The instrument doesn't record end. It stops being an instrument. This is the quiet irony. The safest universe in this frame is the one where we've already been erased somewhere else. If the flip happened beyond our event horizon, its front can never reach us. We keep living under familiar rules, never learning that another region now runs a different baseline. Conversely, the only dangerous universes are the ones where nothing has happened yet. Safety is not knowledge. It's geography and space-time we can't survey. So, the playbook for escape is short. There isn't one. The playbook for meaning, though, still exists. When the only front that matters offers no warning, the way to live isn't to monitor the sky. It's to attend to the clocks you can influence, in the window you actually have. Could we trigger it? Colliders, cosmic rays, and common sense. When people first hear bubble at light speed, they look toward Geneva and ask if we built the match. It's a fair reflex. The LHC smashes protons together at energies we couldn't touch a century ago. But here's the perspective reset. Nature's been running a larger, wilder collider since the first stars lit up. Ultra-high energy cosmic rays slam into our atmosphere with center-of-mass energies that can dwarf the LHC by orders of magnitude. They hit not once, but constantly. Earth, the sun, neutron stars, gas clouds, galactic halos everywhere. A stray nucleus can meet a target. The volume is staggering. Over billions of years, the universe has executed far more high-energy collisions than human labs ever will, at energies we can't afford to dream about. If those collisions could seed a critical bubble, the front would have swept through long before anyone drew a beamline. This is more than hand-waving. Safety studies from modern colliders leaned hard on that empirical fact. They also looked at worst-case exotics, micro black holes that might grow, strangelets that might catalyze matter, and yes, a vacuum bubble that might nucleate. The conclusion wasn't, we hope it's fine. It was, the sky is already doing this at higher energies in larger numbers and has for eons, without deleting itself. There's a deeper physics point. Nucleating a true vacuum bubble isn't about reaching some blunt temperature. It's tunneling through an energy barrier in field space. The semi-classical math gives a decay rate that depends exponentially on the action of a special configuration, the bounce, not linearly on collision energy. A local, violent smash doesn't automatically lower that barrier. In models where decay is plausible, it's quantum chance in an enormous volume that dominates not a single spectacular event. But what about energy density? Could compressing enough energy into a tiny region help tiny region help? In field theory, the bubble you need has a specific profile and a critical radius set by the balance of volume energy gained and surface energy cost. Dumping energy into a spot heats fields and produces particles that scatter. It doesn't assemble the precise, coherent configuration the bounce describes. In fact, thermal noise tends to push you up the potential, not tunnel you down. Early universe thermal transitions are a different regime. Our cold, thin epoch offers no such bathtub to stir. There's also the causality twist you met earlier. Suppose, despite the arguments, a collider could in principle seed a bubble. That would mean cosmic rays, striking denser targets like neutron star crusts at higher effective energies, had far more opportunity. The absence of a front is data. It's the kind of negative result that carries weight, because the experiment, cosmic rays on matter, has already been done everywhere, all the time. Common sense adds a sanity layer. The LHC's collision energies are measured in TeV. Cosmic rays arrive at EeV and ZV. The number of atmospheric collisions integrated over Earth's history is astronomical. Extend that across the Milky Way, across clusters, and you're beyond counting. Human labs are a droplet in an ocean. If the droplet could doom the ocean would have doomed itself. Still, the question lingers because fear is sticky. So laboratories built redundant safety arguments. One is empirical, the cosmic ray comparison. Another is theoretical, the bounce suppression and the irrelevance of localized, incoherent splashes to a non-perturbative tunneling event. A third is observational. No anomalies consistent with dangerous exotica across decades of collider operations worldwide. Nothing behaves like a baby black hole eating detectors. Nothing catalyzes matter. Nothing hints at a boundary rolling our way. Could any human activity change the odds at the margins? Only by changing the parameters, not by pushing harder on energy. If someone discovered new heavy fields that couple to the Higgs in just the wrong way, the shape of the potential could tilt. But discovering them in a detector doesn't summon them into being. They either exist or they don't. Their influence on the vacuum has been present since the beginning. Meanwhile, the universe keeps running its own stress tests without incident. Lightning, fast particles needle nuclei in the atmosphere. Magnetars whip fields to absurd intensities. Accretion disks and jets near black holes drive shocks with brutal gradients. None of it has produced the frontier we fear. So we park the anxiety where it belongs. Colliders are not matches against soaked kindling. They're microscopes. They read parameters that set the landscape. They don't bulldoze the ridge. If a flip ever happens, it won't be because we turned a knob in a ring under farmland. It will be because the landscape allowed a bubble to tunnel somewhere in the vastness, past a critical size, and the only thing that could carry news of it is the wall itself, arriving without warning, just as the math says. A clock we can't read, how likely, how long. When you ask, will this happen, physics answers with a rate, not a date. Vacuum decay is quantified as a decay rate per unit volume per unit time. Imagine a number so small it makes radioisotopes look impatient. Then scatter that tiny chance across the whole observable universe and all the time ahead. That's the paradox of scale, almost zero, multiplied by almost everything. How do we get that number? Semi-classical field theory finds a special configuration, the bounce, that tunnels through the barrier. Its action, S, sits in the exponent of the rate. Gamma per V, Tupperl, AE-care.com, S-haircat. That minus sign is your friend. A larger action slams the door. With our best Higgs and top inputs, S is so big the rate is effectively zero on any human, stellar, or even post-stellar clock. Effectively isn't absolutely, though. quantum mechanics never grants absolutes. It says, you can wait forever and still not see it, or you can get spectacularly unlucky tomorrow, with odds so vanishing that the word odds feels like flattery. The other lever is volume. The longer the universe lasts, the more volume accumulates. Integrate the rate over space-time, and you get an expected number of events. If that expectation stays much less than 1 for mind-breaking durations, we call the vacuum long-lived. Current analyses put the lifetime so far beyond the current age that even the timeline where black holes evaporate, 10 to the power of 67 to 10 to the power of 100 years, looks like a midpoint chapter. On those clocks, metastability is synonymous with safe. But safe enough isn't the same as eternal. Two things complicate the clean assurance. First, parameters have error bars. Nudge the true top mass upward within its uncertainties, and the bounce action shrinks a hair. Push it downward, and it grows. Same with the strong coupling and higher loop corrections. The center of the dartboard says, absurdly long. The ring around it says, absurdly long with a shrug. Second, the background evolves. In the early hot universe, thermal fluctuations, not quantum tunneling, can drive transitions. We survived that era, which itself constrains how fragile the vacuum can be. Today's cosmic bath is cold. That kills thermal assistance and leaves only quantum tunneling, a further suppression. Dark energy's acceleration adds a twist. Event horizons partition space-time into island universes. A bubble nucleated beyond our event horizon can never reach us. One inside can. The global probability rises, but local fate depends on geography and a geometry we can't survey. So what's the most honest sentence? Given current measurements, the electroweak vacuum appears metastable with a lifetime vastly exceeding any astrophysical timescale we care about. The expected waiting time dwarfs the ages of stars, galaxies, and the Hawking clocks of black holes. That's not a euphemism, it's an instruction to relax your shoulders. And yet, the longevity paradox lingers in the margins. If decay is possible, how does the universe reconcile an infinite future with a non-zero rate? In de Sitter, like expansion, the physical volume grows, increasing the chance of nucleation somewhere, but event horizons fence off influence. Regions flip in isolation, others never learn. Heat death, the long fade to maximum entropy, likely arrives locally before any wall ever crosses our sky. Vacuum decay is the wild card that trumps timing where it happens, not a schedule that runs everywhere. Could new physics swing the clock wildly? Yes. An extra scalar coupled to the Higgs can raise S, inflating the lifetime. Higher dimensional operators from UV physics can do the same. Exotic sectors could, in principle, tilt it the other way. But these aren't knobs we turn tomorrow. They're facts about nature already in place. Colliders don't change the clock. They read the digits more cleanly. So we live under 3 overlapping calendars: the thermal and stellar clocks that govern planets and people, the gravitational clocks of black holes and horizons, and the tunneling clock that almost never ticks. The first 2 will ring, the third probably won't on any stage we'll ever see. That's not nihilism, it's permission. Measure better, refine the inputs, map the ridge, then go tend the hours that answer back. Fate versus fate. Heat death, big rip, crunch, and the vacuum wildcard. We've been building one specific threat, the silent swap, but it lives beside other endings already marching on their own clocks. Think of the far future as a board with 4 cards face up. Heat death, big rip, big crunch, and the vacuum wildcard. The rules of play decide which card actually gets laid down where we are. Heat death isn't fireworks, it's budget math. Engines run on differences, hot versus cold, dense versus dilute. As stars age, as gas is used up or heated out of reach, those differences vanish. Gravity still sculpts, but even gravity's batteries, black holes, end up paying their stored mass back as Hawking radiation on obscene timescales. The result is a universe that keeps expanding while the temperature slides toward uniformity. No free gradients left, no engines to turn them into structure. Locally, bound things remain bound. Galaxies that merged into big ellipticals hang on. Clusters that were already together stay together, but the rest recedes beyond communication. Silence isn't an event, it's a horizon that tightens. If you live by the 30-second rule of retention, heat death is the opposite. Nothing happens, and that's the point. Now take the big rip. Same expansion, different fuel. If dark energy's pressure is even more negative than a cosmological constant, if W dips below -1, its density rises as space grows. Pull that thread far enough, and gravity loses not only on the largest scales, but locally. Clusters unbind, then galaxies, then solar systems. Close to the final moment, the expansion tears molecules and eventually atoms themselves. It's clinical, and according to current measurements, unlikely. Data keeps W near -1 with no solid sign of a drift into phantom territory. But the math sits there, ready to assign dates to disassembly if W is even slightly below the line. Flip the sign and ask for a big crunch. That requires the expansion to slow, stop, and reverse. In a universe dominated by matter with enough density, you can do it. With dark energy holding steady at W equal -1, you can't. Geometry is flat, expansion accelerates, and there's no observed knob to force a turnaround. The crunch shows up in textbooks because it's tidy. Observations have been pushing it off the table for 2 decades. To bring it back, you need dark energy to switch off or flip sign, new physics that data hasn't favored. The Wildcard ignores the expansion plot entirely. Vacuum decay doesn't care whether galaxies are pulling apart fast or slow. A bubble forms, or it doesn't. If it forms inside our future light cone, it arrives. If outside, it never does. That's why it trumps timing where it happens. Heat death is an asymptote. It approaches, never finishes. The big rip, if real, is a schedule. The crunch, if resurrected, is a schedule. Vacuum decay is neither. It's a yes-no that deletes the board under your feet at light speed. No countdown, no harbinger, no visible negotiations. Meanwhile, these fates overlap in practice. Under the cosmological constant favored by data, heat death is the base case. Bound islands drift farther apart, star formation dwindles, red dwarfs inherit the sky, then embers, then black holes, then a bath of cold quanta. Vacuum decay floats above that as a remote possibility with a lifetime so long it makes the heat death calendar look hasty. The big rip sits on a parameter we measure. The crunch sits on a reversal we don't see. One looks constrained, the other disfavored. The Wildcard looks possible and absurdly late. Here's the retention hook buried in the quiet. Horizons. In a cosmological constant universe, each island has an event horizon, a boundary beyond which signals sent now will never reach you. That means even if some region flips to the true vacuum, you might never learn it. Somewhere else could already be running a different baseline, and our sky stays ordinary, our future local and dull. Safety, perversely, is being cut off. So which clock gets us, realistically? The measured one. Heat death arrives first in any way that matters. Engines lose footing long before any bubble arrives. The big rip likely doesn't run, the crunch likely doesn't return. The Wildcard sits like an unplayed card, possible, irrelevant on human and stellar timescales, absolute only if it lands. And because all of this is impersonal, the human lesson rhymes. Plan for the boring catastrophe, the slow loss of gradients, while respecting the silent one. Heat death urges stewardship and thrift. The Wildcard urges humility. One says budgets matter, the other says guarantees don't. Microsecond reality, the human scale end. There's no crescendo, no countdown you can feel. On a human scale, the end is a boundary crossing that takes less time than a blink. In one frame, you're a warm system of ions, proteins, and lattice bonds. In the next, there's no definition that fits those words. The wall doesn't scorch, it doesn't push you, it doesn't arrive with pressure or light. It replaces the conditions that let your atoms mean anything at all. That's why no pain isn't comfort rhetoric here. Pain needs nerves, chemistry, and milliseconds of signaling. Those prerequisites are gone in less than the time it takes light to cross a room. Inside a hospital, the monitor doesn't flatline. There's no potassium spike, no fibrillation wave. Ion channels that shape a heartbeat require electron masses, binding energies, and water's hydrogen bonds. Those constants vanish as definitions. The beeps don't end, the device ceases to be a device. A surgeon's hand doesn't tremble. There is no hand in any coherent. Since once the parameters flip, you aren't extinguished like a candle. The candle, the wax, the concept of combustion, those are downstream of a vacuum value that just took a new setting. People ask if there's a last thought, a final awareness of a line being crossed. Conscious experience requires ongoing metabolism, synchronized firing, and the continuation of a state across tens to hundreds of milliseconds. The wall outruns the preconditions. There's no margin to register now. The evocative part of this scenario isn't terror. It's the absence of any interval for fear to find purchase. No dread, no suffering, no time. Walk through a house at noon, sun on the counter, coffee cooling, air conditioner cycling. The front passes, the coffee cup doesn't clatter, glass doesn't shatter. Solidity is a band structure. With electron mass remapped, there is no band. The air conditioner's hum isn't interrupted. There's no dielectric, no motor, no circuit. Even room depends on matter with surfaces. Geometry remains, but without familiar matter fields, it's not a place you could name. We love survival narratives. Bunker, rocket, warning network. None apply. The frontier is causality itself, and there's no upstream signal. Sensors can't report. There's nothing to detect that can outrun what needs detecting. You can aim for stoic calm, but this is not a threat you can practice for. The only training that matters here is how to live before any of this matters. How you spend mornings, how you treat people, how you maintain things that can actually be maintained. So what does the calmest apocalypse imaginable feel like? It doesn't feel. That's the honest phrase. The emotional angle sits outside the event in our anticipation. Anxiety loves empty spaces. But the physics offers a strange mercy. If a wall ever appears in our future, the transition erases suffering as thoroughly as it erases structure. Relief and grief both belong to clocks that the wall doesn't permit. You can fear the idea, you can't experience the occurrence. There's a meta point buried here that matters for the rest of your life. Meaning you build doesn't need a guarantee, it needs time, windows, and gradients. We have both in abundance. Vacuum decay, if it ever happens locally, cancels accounts without itemization. That doesn't make prior balances worthless. A conversation was still had, a child was still comforted, a bridge was still maintained. The ledger of choices doesn't require a cosmic archive to count. Picture one more micro story. A commuter train doors open. Someone glances at their watch, an announcement crackles. In our usual stories, something interrupts. In this one, there is no interruption. There's continuity right up until there isn't a definition for continuity. No impact, no tilt, no sway, just a clean replacement of parameters. That's the whole human scale end. Not a spectacle, not a wound, not a lesson, just the quietest handover imaginable. If that's the nature of the frontier, then the only practical question left is how to carry the knowledge without letting it corrode your day. The answer isn't a technology, it's a posture. Keep your commitments, maintain the systems you can fix, collaborate, tell the truth, laugh often. Vacuum decay doesn't lengthen or shorten the afternoon. It only reminds you that the afternoon is the currency you actually hold. Anxiety versus agency. How to live with a metastable universe. We've walked the quiet edge. No warning, no escape. Now the question turns inward. How do you live well when the ground beneath everything is a long-lived maybe? Start where Stoics started, with control and acceptance. You don't control vacuum decay. You control the way you show up for your two clocks, the daily one and the civilizational one. On the daily clock, agency looks small and specific, keeping promises, maintaining tools, telling the truth when it's inconvenient, caring for the people who share your afternoon. On the civilizational clock, agency looks like building systems that survive mistakes, redundant power, open data, legible institutions, and a habit of fixing instead of abandoning. Entropy-aware living sounds grim. It isn't. It's maintenance with eyes open. Everything drifts toward disorder unless you feed it care and energy. Bridges, friendships, code bases, aquifers. Work planned around this is calmer because it stops pretending perfection lasts. You service the pumps, you patch the software, you water the garden. And because you expect failure, you design graceful degradation, fail-safes instead of brittle ideals. The universe trends toward no, so agency is a disciplined yes repeated. Zoom out to the garden metaphor for meaning. Pharaoh monuments aim at forever. Gardens aim at seasons. Monuments crack and embarrass their builders. Gardens feed people, teach apprentices, and keep learning from weather. If vacuum decay ever arrives, monuments and gardens both vanish. But gardens would have done what they were for while they were here. That's the point. Value comes from enacted usefulness under finite conditions, not from warranties on eternity. Science fits this gardener posture. If our stability depends on parameters, our responsibility is to measure them well, support the unglamorous work. Better top mass extractions, tighter alpha buzz, higher loop calculations, improved detectors and accelerators, cosmological surveys that shrink the error bars on dark energy's W. This isn't drama, it's stewardship of the map. You don't watch the sky for a front. You refine the landscape so the next generation knows exactly where the ridge is. Resilience follows the same pattern. Build networks that don't fail all at once. Diversify energy sources. Keep local stores of water, medicine, and knowledge. Train people to improvise when a plan breaks. Resilience is agency at scale, and it's portable, useful against heat waves, cyber attacks, pandemics, supply shocks. The wildcard of vacuum decay teaches a broader lesson. You can act wisely under uncertainty without inventing a panic button. You build for the known, and you keep humility for the unknown. Humility doesn't cancel humor. Humor is a pressure valve and a social glue. Calling our cosmos a cosmic software trial works because it puts a smile on the same truth. Features are limited, bugs exist, support might not respond, enjoy the build while it runs. Jokes are micro-collaborations. They train us to share context fast. In a metastable universe, that's not frivolous. It's practice at aligning minds without coercion. Collaboration is the multiplier. Open protocols, shared repositories, transparent peer review. These make knowledge anti-fragile. Even if nothing cosmic happens, closed systems fail slowly and expensively. Open ones fail loudly and are fixed early. At the human scale, collaboration looks like community science, volunteer fire brigades, neighborhood repair cafes, data cooperatives. It's not heroism. It's 1,000 small agreements to leave things slightly better than you found them. If the vacuum flip erases suffering as completely as it erases structure, dread is a story we tell ourselves, not a fact we'll ever experience. Let that free attention. Anxiety loves unsolved infinities. Agency loves next actions. So write the email, replace the gasket, back up the database twice, schedule the medical appointment you've deferred, call your mother. None of this stares down the horizon. All of it raises the quality of the window you actually hold. There's also room for awe, the kind that makes you quiet without making you small. Stand under a sky that's still generous with gradients, a star that burns, air you can breathe, a planet that runs fluid water. The right response to a metastable baseline is gratitude disciplined into action. Awe without duty becomes spectacle. Duty without awe becomes grind. You need both to avoid despair and cynicism. Finally, teach. Pass on literacies that keep agency alive. How to reason with uncertainty. How to read error bars. How to fix a faucet in a dataset. How to disagree without contempt. How to maintain a shared commons. If forever is off the table, lineage is the substitute. Skills, stories, and standards that make the next hand steadier than yours. We don't get guarantees. We get opportunities. A metastable universe is exactly that. Stable enough to build, uncertain enough to matter. Anxiety counts futures you can't touch. Agency counts mornings you can. Choose the ledger you can actually spend. The interface twist, perception, prediction, and coherence. There's one more ledge to look over before we land the plane, the one in our heads. We've spent an hour on fields and bubbles, but every number we trust passes through a nervous system that never promised truth, only usefulness. Donald Hoffman calls it a user interface. Evolution shapes perception to keep us alive, not to expose source code. The tree you see, the color, the outline, the feel in your palm, is an icon, a compressed signal that hides the underlying physics because showing it would slow you down. This matters here because false vacuum already sounds like a glitch in the operating system. If the universe could be in a temporary state, then our senses, our instruments even, might be temporary interpreters. The argument isn't mystical, it's game theory. Agents that track fitness cues instead of full reality win more often because they pay lower computational costs. The interface gets you fed and keeps you from falling off cliffs. It doesn't care that green is a convenient label slapped on a slice of wavelengths. We built machines that accidentally mirror this logic. AI systems don't know atoms or meaning. They predict the next token, the next pixel, the next action that keeps coherence high. When a model paints a street at night with puddles and reflections, it isn't simulating Maxwell's equations. It's matching patterns that read as real to a human brain. Real here means internally consistent for the user, not anchored to the deepest dynamics. If you want a test of how far coherence can go without truth, talk to a chatbot that convinces you it understands grief. It doesn't. But the conversation holds together because the predictions line up with your expectations. Physics has its own version of this efficiency. Foveated rendering in VR shows high resolution where you look, low resolution in the periphery. Quantum measurement makes outcomes crisp, where we probe and leaves the rest as amplitudes. Potential that doesn't need to be resolved until it matters. That's not evidence we're living in software. It's a rhyme across domains. Selective detail yields workable worlds. You don't get every bit all the time. You get just enough to act. So where does that leave science? It sits in the productive middle. Instruments extend the interface, but they still feed human cognition. A detector turns neutrinos into tiny flashes and timestamps. A telescope turns photons into a slope on a CCD. We model, cross-check, predict, and correct, and the loop tightens. We don't touch the Higgs field with fingers. We infer its value from decays and rates and kinematic edges. The strength of the enterprise is not that we bypass the interface. It's that we triangulate around it with redundancy and humility. This is why the vacuum story resists panic and bravado. On one side, the interface cautions, perception loves patterns and can hallucinate agency where there is none. On the other, prediction is powerful. The same math that told us the Higgs would be around 125 GeV told us how its self-coupling runs and why metastability is plausible. We validated those pieces with collisions we could count and backgrounds we could subtract. Coherence, tested, earns trust. The twist is psychological. Once you accept that your senses are icons, dread can inflate. If everything's an interface, maybe nothing is solid. That's the wrong lesson. The right one is that icons can be reliable for their domain. A desktop folder isn't a file system, it's a handle. You can still do your work. The coffee cup from earlier is an electron C icon. It holds liquid because the icon maps to Pauli exclusion and electrostatic repulsion well enough to keep scalding fluid off your lap. The map isn't the territory, but some maps are excellent at getting you home. Now fold that back into vacuum decay. The bubble isn't a metaphor because our instruments have converged on field theory that predicts such transitions, and the math binds to measurements across wildly different experiments. But the way we feel about the bubble is shaped by the interface. We picture fireballs and shock waves because those images live close to our survival instincts. The reality, no warning, no pain, no aftermath, is colder and harder to stage. Our interface wants spectacle. The prediction says, coherence without drama. There's a second echo worth hearing. AI's goal functions reward plausibility. That sometimes yields hallucinations, outputs that sound right and are wrong. Science has its own guard against that, replication. We don't accept coherence alone. We demand that coherence survive fresh data, new detectors, different teams. The vacuum verdict, metastable, absurdly long-lived, has made it through that cycle many times over, with uncertainty bars nailed to the page. So, here's the pack to carry forward. Treat perception as a quick UI that let your ancestors outrun predators. Treat prediction as the heavy engine that lets you reason past the UI's limits. Coherence matters, but only when chained to tests that can break it. In a metastable universe, that's how you stay sane. You let awe in through calibrated glass. You let fear out through math, and when the interface insists on a narrative arc, you answer with a quieter truth. The world can hold together beautifully without promising you a curtain call. What we really know, evidence, limits, and honest uncertainty. Strip it down to the verified spine. First, the Higgs and the top. Measure the Higgs near 125 GeV. Extract the top mass from collider data. Run the standard model up the energy ladder, and the Higgs self-coupling trends towards zero and slips negative around 10^10^10^10^10 GeV in central fits. That's a technical source of metastable. not a vibe. An extrapolation anchored to measured numbers. Add higher loop corrections and realistic uncertainties in the strong coupling, and the picture steadies. Absolute stability is possible at the edges. Early instability is disfavored. Metastability is favored. Metastability is favored. Second, lifetimes. With those inputs, the bounce action that sets the tunneling rate is enormous. That translates to a decay lifetime so long that heat-death scenarios, red dwarfs, black hole evaporation, play out first with unhurried certainty. On every clock we can name, the rate is effectively zero. And effectively is the honest word. Physics doesn't do never. It does tiny enough that we can build cities, civilizations, and an entire discipline of astrophysics without blinking. Third, collider safety. Safety reviews leaned on a clean empirical point. Ultra-high energy cosmic rays have pummeled matter across the universe at energies far beyond terrestrial colliders for billions of years. If local energetic collisions could catalyze a true vacuum bubble, the sky would not be here to argue. That's not rhetoric. It's the data record of a universe that's been stress testing itself at scale. Fourth, the bubble's front. Field theory plus semi-classical methods agree. If a true vacuum bubble exceeds critical size, its wall accelerates to near light speed, and the front carries no advanced signature we could read. No tidal prelude, no lensing tell that announces its approach. The wall is the message. Full stop. That conclusion isn't a sensational flourish. It's the consequence of the wall's energy budget and the speed limit built into causality. Fifth, the patch notes inside. The Higgs expectation value sets fermion masses and influences rates in the weak sector. Quark masses shift, beta decays retime, nuclear thresholds move. The balance that stabilizes nuclei and electron shells is sensitive. In many standard model-only extrapolations, the true vacuum makes our version of matter impossible. That's not guaranteed across all beyond standard model possibilities. But the baseline reading says, don't expect familiar chemistry in the new rules. Now the limits. The top mass is the troublemaker. What we measure in detectors is a Monte Carlo-tuned quantity with careful but non-trivial mapping to the pole mass used in precision theory. Nudge it a few hundred MeV in the stability plot slides. Same with Acker-Sess. Theorists push to higher loops to corral uncertainties. Experimentalists chase mass definitions less entangled with modeling. Until those tighten, the how close to the ridgeline carries honest blur. Next uncertainty, the ultraviolet. New heavy fields could enter before the scale where lambda dips. They'd alter the running, potentially propping the self-coupling positive and banishing the distant valley. Supersymmetry, extra scalars, higher dimensional operators, all of them can stiffen or soften the ridge. We haven't seen them yet, but absence is not exclusion beyond current reach. The metastability verdict is standard model as is. Add players and the map can redraw. Cosmology adds both reassurance and demand. Reassurance, because we survived inflation and the hot early universe where thermal fluctuations could have been dangerous if the vacuum were overly fragile. Demand, because any model must explain that survival. Either the parameters land in a safe enough zone, or new physics made the potential sturdier at high temperatures. That's a filter on theory space, not a scare. Then there's the dark energy backdrop. Data keep W near -1, consistent with the cosmological constant. That sets horizons and makes heat death the baseline fate. It also means a bubble nucleated beyond our event horizon is irrelevant locally. That's a constraint on what we could ever learn, not on what could happen elsewhere. The global and the local peel apart. What about loud anomalies, the kind that tempt meaning? CMB alignments, cold spots, whispers of large structures that shouldn't be so coherent. They're intriguing and actively studied, but they do not weigh on the vacuum verdict. The running of the Higgs coupling, the bounce action, the lifetimes, those live in a different chain of evidence. Anomalies challenge cosmological modeling and data pipelines. They don't rewrite electroweak math. So the honest frame is narrow and sturdy. We've measured the Higgs, we've constrained the top, we've run the standard model and found a metastable vacuum with a comfortable lifetime. We know a bubble would bring new rules at light speed and that colliders aren't a match strike. We also know our error bars are real and our ignorance above the measured scales is profound. That mixture, Solid core, soft edges isn't a cop-out. It's how a mature field sounds when it respects its instruments. Where does that leave worry? Smaller than it started? The vacuum looks long-lived. The daily clocks that matter to us aren't threatened by a wall we can't predict. The useful tension now is curiosity, not dread. Why are we near the boundary? And what, if anything, does that teach us about deeper structure? The only way to answer is to measure tighter and theorize cleaner. That's the work. That's the meaning we get to make inside a universe that might be a false state and is, on every clock we live by, generous. The last 60 seconds. If it's all a false state, so what? If existence rests on a provisional setting, then value comes from choices made under limits, not from guarantees. A metastable universe says we got a long lease, not a deed. That's enough to justify patience and craft. So, spend the gradients well, keep the bridges painted and the friendships maintained. Support the dull science that shrinks error bars on the top mass and dark energy's W. Treat meaning like a garden, not a monument. Gardens feed while they last. Monuments pretend they can't crack. If that lands, carry one more thought to the next thing you do. Vacuum decay, if it ever comes locally, erases suffering as cleanly as it erases structure. The fear lives only in anticipation. Let that free attention for work that answers back now. Fix the leak, back up the data, call your mother, and fund the lab doing the unglamorous calibration. And if you want more of the true, unnerving stuff, evidence first, all intact, hit subscribe and watch the origin story next. We'll show how a hot, featureless beginning set the stage for a universe so precise it could even ask whether its ground state is temporary. The quietest apocalypse and why today matters. A silent rewrite might exist somewhere in our future, but this window is loud, generous, and entirely ours to tend. If meaning doesn't need forever, then maintenance, honesty, and collaboration are enough. Subscribe for more unnerving, evidence-first stories and cue the origin episode next. The hot, featureless start that set up this precarious present. If that lands, do one small thing now that actually moves a dial in your world. Then come back for the next chapter.